Alright, once again, for everyone's benefit, there was no video yesterday because we were just trying to get something done in the midst of technological crisis. Chaos. That was an issue. Alright. So we gotta focus on this. Let's go ahead and pay attention. Let's get stuff done. So, section 12.2, we gotta check it. But 12.2, do you remember what was there? The difference quotient was there. One-sided limits were there. And then, simplifying whenever you get 0 over 0 before plugging in again to solve limits was there. So, 12.2, the evens. Here we go. The first four, dividing out, indeterminate, one-sided limit, difference quotient. You don't really need the odds, but there you go. Number 6, A was 0, B was 1, C was -2. Did you guys get down the whole thing? Boards on a graph and looking at it. The limit exists if the one-sided limits. Yes. Just grab one out of the water cooler if you want to step out in the hallway. Oh, sorry, I stressed.
I am so done.
No, you're okay. It's left over from the AP and I just don't want to lug it out because it was heavy now. Alright, come back. The one. No. Okay, the limit exists if the one-sided limits. How does that go again? The limit exists if the one-sided limits. The limit exists if the one-sided limits
approach the same word.
Yes, aka agree. Does that make sense? Okay. No. That's okay. But you had the idea. So the limit exists as x approaches a constant, A or C. Focus. The limit exists if the one-sided limits agree. If the one-sided limits do not agree, then the limit does not exist. And so the limit will only exist if the one-sided limits agree. What if the one-sided limits agree to like infinity? How do I answer that? Yeah, and what are they approaching? Infinity. So we say positive infinity, or what are they approaching? So we say infinity. But if they do not agree to infinity, we still say the limit does not exist because they're going in different directions as you come in. Anyway, long story short, number 6, they all agreed and they all existed. So the limit of A was 0, B was 1, C was -2. Where do we go from there? 10 and 12? 10, the final answer should have been -7. That's just with factoring. 12, with factoring, which was a little bit harder. Technically, you kind of use SOAP. But you could have used polynomial division. I did an example like that in class. Number 12, final answer was 48. Number 16. The final answer, multiplying by a conjugate. Did you guys figure out the difference between factoring and multiplying by a conjugate? What was there in this problem that made us multiply by a conjugate? The radical. Good, the radical says it's multiplied by the conjugate. You end up with 1/8. Number 18, how did you end up at -164 if you couldn't factor or multiply by a radical? What was new in number 18? Number 16, what was new with the radical? And number 18, what was new? Yeah, complex fraction. A fraction and a fraction. Thank you. Alright, so I'm moving on. Number 20, the final answer was -1 once you plug and chug. But some of you, what was new about 20? That was kind of a little puzzle. What did that make you think of?
Properties.
I was thinking it was a little T-proof. Isn't it a little T-proof? Because you had to transform. Change cosecant to 1 over sine, cotangent. That's different. I think she's looking here, but I don't see the little people.
No, wait, just draw like little circles on top of like the little things.
We are so confused.
Stop.
What?
Oh, I pass.
I have no idea.
Look, it's like two.
Oh! I get it. I get it.
What kind of artist?
Look at that. Skills.
Oh, I see it.
Oh,
It's just
haha.
like you take art and how did you see that?
I love it.
Okay. Wait, pause. Come back. Apply that. What? Oh. You thought they were the little people that were like holding hands. Yeah, there's the little feet. Now you see it. Now, I love the creativity. What am I hoping you're able to apply the creativity to?
I'm sorry.
Trig properties. Yay. Okay, question. Did anybody have a question on 20 or did you all get it? Because 20 was kind of hard. Who had a little question on 20? At least at some point during homework. Okay. Liars.
I'm sorry.
I'm so calling you out right now. There is no way every single person in this room totally understood what to do on number 20. But let's just say, do you see now? Come on, I need my honors kids to be honest. Do you see now what the benefit was with changing cosecant and changing cotangent?
Yeah, so you take the cross.
Exactly. So crossing out, changing the form does not always come in the form of factor. It doesn't always come in the form of factor. This one you do is trig proofs, and then yay, the sign crosses out, and then plug it in. Anyway, final answer is negative 26. You just had to graph it and look at it. It was 0. Number 30. You were able to use a graph as well, and I would probably use a table. This decimal you might not have been super familiar with, which is why I put the decimal, but it's also negative 2/3. Number 40, it's a piecewise function. As you come from below, the height is approaching 3. As you come from above, it's 2, it meaning the limit. But as you compare the two, the one-sided limits do not agree, so the limit does not exist. Now, quick question. Do you guys understand why, even though there's a hole there, the limit still exists? Yeah, it's what it's approaching. It doesn't really matter what's there or what's not there. It doesn't really matter what's there or what's not there. The point is the... Does that make sense? The point is the approach. All right, so next thing back. I think we're almost there. 48 and 50 were both difference quotient. How many of you guys would say that yesterday seeing that example helped a little bit? My 3 people, I really appreciate you. But a lot of people weren't necessarily here. So let me talk it out just a little bit. Sadly, the examples. Ooh, hold on. Nope, you got it in the notes. All right.
So they will be in the video.
Now they're in the video. Can someone, he's gone today, he has to go to the Brazilian embassy, somebody.com. Somebody coming back. Coming back. Someone yesterday, there's, question, what does f of x plus h need us to do? In order to plug into this formula, we need f of x plus h. We need f of x, oh, we have f of x. And we need h. The h just goes in, he's normal. The f of x goes in, he's totally fine, he's just the dude that they give us in the beginning of the problem. What's the hard one to find? F of x plus h, exactly. So, we have f of x, that's no big deal because that's the function that they give us, and so we plug it in. Remind you one more time with different colors. We have the h because it's just itself, it just goes in as itself, no big deal. But what's tricky, once again, is the f of x plus h, because we need to take f of x and we need to plug into its argument x plus h. So do you guys see me plugging in x plus h to f? So I plug in x plus h into the place where x was. Anyone who was here yesterday, we did it on the board. But people who are gone, this is mostly for your benefit. We plug in x plus h. We have to do some foiling. I went ahead, unlike yesterday, I simplified it off to the side and then I plugged it in to the f of x plus h spot, which is right here. So then I plugged it into where it's supposed to go. Yesterday, I think we just plugged this in, and then we simplified. Both ways are good. Eventually, once you simplify, hopefully, stuff cancels out. Karina caught this yesterday. She was like, hey, there are h's on both the tops. So you told us to do what? Factor that h out? Yeah, reduced, it's gone. Plug it in. Now, why was there an x remaining? Yeah, h is approaching 0, so Yeah. And so then yesterday we went back to tangent lines and like the parabolas from section 10.2 and how with tangent lines you have this thing called a derivative, and we went kind of deep yesterday, but the nice thing is we get to recap it in section 12. Kiddos with that homework, I believe. Oh, if you want to check the answers. Number 48, final answer should have been 2x minus 3. And then for number 50, final answer was negative 1 over x minus 1 squared. Okay. During the video, if you guys need to see it, we're back to section 12.3. Those of you guys that were gone, how far? I think we just got this page, right? Okay. The few things that we did to learn on this page, we're reminding ourselves that we're back to the tangent line problem. We talked about it in the preview calculus, little snippet before we started chapter 12. In the first graph, these ones are just kind of showing tangent lines and how tangent lines skim the graph. As you guys that were here yesterday, we talked about this. I think you even got most of it down. Tangent lines are just little snippets that skim the graph. At the very bottom, I asked you guys some questions. I asked, what kind of slope? I'm not saying the number, because you can't tell the number just from what's being given. But what kind of number? Positive, negative, 0, undefined. What kind of number is the slope in the first graph? I'll just call it A. Yeah. What kind of slope is in letter B? Negative. And what kind of slope is in letter C? Which one? Yeah, 0. We talked about yesterday cross-country skiing. We had to kind of remind ourselves that if something is flat, it has no slope. You're not going anywhere fast. You're not having to work against anything. You just use friction on the ground. So, 0 slope. You're not undefined. What does undefined slope look like? Yeah, you're undefined. You ski that. So flat, no big deal. No slope. Straight and down. Undefined, technically infinite slope. I'll be super snazzy. This one is 0. 0 slope is when we have what we would call a horizontal tangent line. Let me zoom in on that real fast so I can write it. Horizontal tangent line. And technically, it'll come back that we'll call those HLTs. Now I know we called HLT the horizontal line test, which has to do with whether or not a function is invertible. But like in calculus, we would say HLTs are horizontal tangent lines. They're kind of important because with motion and whatnot, horizontal tangent lines show us when an object is stopped versus when it's moving. If the slope is 0, the rate is 0, the thingamabob is stopped. So that's also why in physics we can say if slope is rate, and if you throw something in a parabolic curve, whether it's like something being shot up and it's coming back down, whether a ball is being thrown and it's coming back down, whether like a sprinkler is shooting out water and it's coming back down. At the very top of that motion, this horizontal tangent line is why we can say that object actually momentarily stops before returning back down in terms of like vertical velocity. That's it. Horizontal. Oh, I did. No, I appreciate that. I did do the horizontal line test instead. That's much less confusing than I thought it was for a second. HTLs. Okay, people who were gone yesterday, did you catch up? Okay. Wait. Can I show you guys the notation? I think it's coming up in the future. Let me get my notes. Actually, I'm going to open it. So I'll do that while you guys work. Oh, computer. Look at this. Do you see this? Working on it. Tangent slopes. We've already talked about this just a little bit, so I'm going to kind of fly through because it's not a huge thing that I think we need to recap. But the dilemma of a tangent slope, or of a tangent, the slope of a tangent line, is that a tangent line hits a curve, I don't know, like a circle from geometry, hits a curve how many times in like that local area where it's going across? Once. So a tangent line hits at one point. Like one point. So what's the dilemma of a tangent line only hitting at one point, so we only know 1 point of a tangent line? We need 2 points for a slope. That's the dilemma. That's all I have to fit in. The slope needs 2 points. Why? Because old-fashioned slope equals rise over run, and to get rise over run, you need to have 2 points. True? This is technically what we would call if we are... This is technically what we would call if we were solving, remembering that slope relates to rate of change. That's why slope technically is just an average rate. So it's on average over 2 times, or on average over a distance. An object has to move a certain distance in order for us to be able to approximate its rate without calculus. But what if we had like a really precise picture and we could just look at the picture and sketch the tangent line and then kind of just look at it visually and approximate the slope? Now, this is not ideal. This is not precise. And if you draw a tangent line, you'd have to get a ruler, like a straight edge, and then be like, okay, exactly where do I put it? You could actually kind of draw different slopes. So if you were drawing a tangent line, it would be really imprecise. But if they show you the tangent line, how could we visually approximate? Well, they've shown us the tangent line. Do you guys see it? They've shown us the tangent line they care about in this one. So I could say that the slope of x squared at x equals, what point of tangency are we talking about? First, the point is just at x equals 1, is 2 over 1, right? So remember, rise over run. So if you want to think of it, you can do 2 over 1 that way. Or if you can think of it this way, it's the rise over the run. So they show us the rise is 2, they show us the run is. And maybe we could kind of approximate that ourselves and say, hey, it looks like 2 hits at 3. So we could almost do the slope ourselves. If we can see it, we can approximate it and say, I think I know the point-ish, but it's not. But especially when they show us this little triangle with everything matched, we can say, oh, okay. So if the slope of x squared at x equals 1 is, and that's also the same thing as the slope of the tangent line. There are 2 different ways of saying it. Both ways have their benefits and different applications. But the slope of the tangent line at x equals 1 is 2. I'm just giving you wording just to kind of hopefully flush it out just a little bit better as to what's really going on. So I guess you could visually approximate the slope of zooming out for anyone that missed anything above. We could approximate the slope of our function at a point by looking at it. The problem is, without having an equation of a tangent line, we can't necessarily make our grapher show us. We can have it show us the function, but we would still have to get a ruler and kind of hold it up and be like, it's giving it kind of, but is that right, or is that right? It gets a little bit tricky. So once again, this is not an ideal situation, but it is one way of approximating the slope of a tangent line, especially if they give you the picture so you know it's perfect. However, we got to move past that. In order to move past that, we talk about the secant line. And the nice thing is, you guys have technically already drawn this picture if you drew it back when we did the tangent line problem originally. So you don't necessarily have to draw this picture again if you don't want to. You don't necessarily have to draw this picture again if you don't want to. The point is, in order to build up to the calculus, and you kind of saw the illustration earlier, is that to approximate the slope, drawing it and looking at it isn't very valid unless they give you the perfect picture and they know what the tangent line is supposed to be, which we don't usually like to work backwards from solutions. We'd rather be able to get there on our own. So if we have to get there on our own, the only way that we can actually tangibly talk about slope is slope between 2 points, aka slope of the secant. So secant line, remember, cuts through 2 in a certain local area. It might cut through more down the line as the curve does, like loopy loops or something. But secant line in a local area, we have it intersecting the curve in 2 places, which would then allow us to find the slope the old-fashioned way. But I'm showing you not y2 minus y1 over x2 minus x1. I'm showing you the notation from up above where h was delta x, and we might want to write that off to the side just to help us visualize exactly what's going on. From this little diagram, we can say h is delta x, which is y down here. That gets plugged into the change in x spot. And that's also why if you start at the point of tangency x to go to the new x for a second point, you have to add h. And that's what's in the difference quotient that you've kind of gotten a little familiar with. And that would be the second y, and the first y would be the original f of x of the point. So I'm going to zoom in on that picture just for a second. If you want to get the visualization, it helps you know who are the players in this equation down here. It all comes from thinking about a point of tangency. We're going to go ahead and show the tangent line approximately. The tangent line hits at one point. And so we use that one point as the x1, y1. And then we go ahead and use that h to move away on the x and move away on the y to get that second point. But once again, guys, this is a lot of notation. But we have called this formula in the past, and I've used it a couple times even today. What's the name of this formula that I've circled down below? Good. That's the difference quotient. That's the difference quotient. So average rate. Slope as we know it is always between 2 points. Not that you necessarily have to write that, but that's what we're modeling here, that, oh, okay, well, as long as the slope is in between 2 points, okay, we got that. The difference quotient is a generalized y2 minus y1 over x2 minus x1. So, tangent line, if they give us a nice picture, I guess we can kind of guess, but that's not a super hot idea, and if they don't give us a picture, then we're totally stuck. If we do actually have to work with the slope ourselves, we'll stink. The only way we work with slope is with the y2 minus y1, but so far we've attached that idea to the difference quotient. We've attached that idea to the difference quotient from which, well, maybe using a limit, now you don't have to write this. Using a limit, we can go ahead and have the h's get smaller and smaller and smaller. And as the h's get smaller and smaller and smaller, this was the visualization that we saw at the beginning of the notes for the previewed calculus. As the delta h gets smaller and smaller and smaller, what's happening with those secant lines? Exactly. They're getting closer. And what's the size behind? Where are they getting closer? Approaches. Hey, that's a limit. Okay, so let's figure out exactly how this limit thing works. Let's see if I have this up on the screen. Let me have you guys, as I get this up on the screen, write down this important box. To find the slopes, not with a picture and like a ruler, and kind of guessing-ish what it looks like. It can be really imprecise and pretty difficult to get precise. We need a limit. We need our secant lines to approach our tangent line and see if we can solve using a limit for the slope that we truly seek. This difference quotient is super important once it gets down to solving for the slope of the tangent line, which forms the foundation of calculus, or at least one of the main pillars. So not only do you have to know, like, I don't know, algebra 2 pre-calc, algebraic manipulation to do your function notation, but you also have to know limits, and then you have to realize, hey, that's a derivative. It's a huge, huge problem. Let me show you a quick illustration using a demonstration. If you guys have ever asked Siri a math problem, has anybody ever asked Siri a math problem? You should try. She's actually pretty good at math. Do you know why she's pretty good at math?
She's a computer.
No, not that she's a computer. They've actually gotten the rights in order to use Wolfram Alpha. They've actually used Wolfram, or they've they have Siri accessing Wolfram Alpha in order to be able to do math, basically. Wolfram Alpha allows you to do all sorts of crazy stuff. You can only ask it so many questions a day, sadly, because they realized they had something good going. But they do have really cool demonstrations that try to show us different calculus concepts. Do you guys see the tangent line? Yeah, we'll start over there. Do you guys see the tangent line that's trying to be depicted in this picture? Who is it? The red line, right? The one going through Q and Q only. You have this e to the negative x graph. You have this tangent line hitting at only one point. So what's this brown line? It's a secant line. Does that make sense? It hits at one point of the curve and at another point of the curve. And then what's this slider supposed to be showing you? It's using algorithms in order to basically find the slopes very, very quickly in between 2 points. See, it's finding the slopes. And what happens as that gets closer and closer and closer to the line? The secants are approaching the tangent. Now, this one sadly goes the other direction as well, and now we're getting lots more error. But the point is, as P comes into Q, kiddos, look at that secant slope. Can you approximate, just by looking at what that secant slope, the bottom brown one, is doing, can you approximate the slope of the tangent line? Oh, now it's not working on the slider. What's it seem to be approaching? Right?
Yeah.
Sure seems like -1. Now, would that math be fun to do by hand? Oh, you know the decimals you'd have to be plugging in and getting out? No way, Jose. Hence why we want the limit formula, because we can do that. We actually have already found derivatives in the last section, and we didn't even know it. Well, some of you did, because I talked about it yesterday. The rest of you guys didn't know it. In order to find the slope, in order to do what would take so much by hand work and calculation. Anyway, coming back. It's great. In order to find the slope of the tangent line, we use this formula. And I want you to go ahead to write down the words as to what this notation means. You could say F apostrophe, you could say F quote, but neither of those are true. We need to call this F prime of X. So it's still function notation, but it's no longer F of, it's F prime of. And F prime of denotes, one more time, the slope of a function at one point, aka the slope of the tangent line, aka the derivative. Oh, no, we're going back. F prime of X, aka the slope of the tangent line, aka the derivative. We ask calculus kids how important are derivatives. Yeah, they're really important. But all they are is a limit. Oh, we're doing limits. Oh. Yeah. Because you didn't have any, like, basis to even think about it. You know what I mean? Yeah, we can't do it. It sounds like, oh, it's a tangent line. Okay, yeah, we can't do that with normal, like, old school math. Because we need 2 points. But if we take a limit, it'll do the whole, like, 2 points, a secant line approaching a tangent line for us. It'll have the distance between the two approach 0. We can just kind of solve the problem and have it do all the crazy math in the process. Now, there are a couple different variations of this formula. You guys don't have to write the formula again. Can you just pause for a second? And can you make sure that you write down the slope at any point? If you have the formula from the page before, I want you to say that this solves for f prime of x, which is the slope. If we write it here, we don't have to write it again. At any point. And that was yesterday when I showed the kids that were in here, that one that we did where the answer was 2x. I actually went on a calculator where you could hit the n derived function, because you can do derivatives on your calculator, 2 functions at points using math. Well, using the graph. I can demonstrate that maybe tomorrow another time. But we saw that the 2x actually shows all the different slopes of all the different tangent lines of x squared. Which means 2x, plug in 1, hey, the slope was 2. 2x, plug in 2, hey, the slope at 2 was 4. 2x at 3, oh, hey, the slope is 6. So it's a formula that you can plug in any x value and find the slope at any of those x values. So it's an equation, it's a formula that we can plug in any x to get the slope of the tangent line at that point. But there is also another variation too. Let's go ahead and cross this off then, because we just wrote all that. There is another variation to this formula where you have an actual x plugged in, not just x, the general and not ambiguous, but the general variable, but you have a specific variable. So it would be at a specific point, and the point would be at the point C, f of C. So if you wanted to find a tangent line at just one point, and there was no purpose to finding a formula that could solve for lots of tangent lines at lots of different points for a function, you're like, I only care about one. Technically, you could use this other variation as well, where you, instead of plugging in a general x, you plug in a specific x, you plug in C, and it would just go in the x bar. So notation-wise, we could actually call this f prime of, how would that notation go? X isn't in there, who is? It'd be f prime of C, which would be talking about f prime of C, the slope at C, which in broader context, the rate at C. So kiddos, looking at the example below, we have two options. They do want the slope at one point. So could I do the general formula and then plug in x equals negative 2 at the very, very, very end? The answer is yes. Or could I use the alternate form and plug in 2 at the very, very beginning and only be solving that one problem and being done? Yes. Just to show you that it does work, yesterday we actually saw that the slope's 2x squared. We already saw that f prime of x equals 2x. It was the last difference quotient that we solved. I think we actually did x squared minus 1. But the derivative will be the same. So I can go ahead and show you f prime of x will be 2x, and once you learn the formula that lets you jump, the shortcut formula lets you jump from there to there, this problem would be pretty easy, because then if I want the slope at negative 2, you would just say, okay, cool, plug in negative 2. What would the answer be? Negative 4. So once you learn the shortcut formulas for calculus, it's like, okay, I assume you know those formulas really well, and then I can actually take derivatives really fast. But I'm trying to show you how the limit formula works. So let me show you how to find f prime of negative 2 using this alternate form up above. So we would say the limit, as h approaches 0, of f of, who's my c? Negative 2, because that's my exponent. Oops, plus h. Minus f of all over h. Okay, now use your algebraic knowledge. Don't find the limit first, because right now if we plug in, we're just going to get 0 over 0, which means keep going. So how do we keep going? How do we change up this notation and make it specific to the example that we have? Yeah, we do know f of negative 2. Isn't f of negative 2 just the y value? So we can plug in 4 right away. Who else though do I need to figure out? Who's missing in my formula? Do you guys see what I've done so far? I plugged in f of negative 2, which is the y value at negative 2. I stole from the point. Rewrote the h, rewrote the limit as h approaches 0. What's supposed to go in this spot? Who's that? x squared. Exactly. F is x squared, but who are they saying to put in instead of x this time? So who am I going to put in that needs to be squared? Does that make sense? So f of says, look to the function. It's like, okay, there he is. Do what to the function? Plug in the new guy. Negative 2 plus h is just a new input, so we put it in the input spot. So input squared is negative 2 plus h squared. Now, the sad thing is, kiddos, nothing's gotten canceled. We've just rewritten. So if we tried to plug in right now, we would get 0 over 0 again. It's because we still need to keep going. What can we do now that we have it all like written down as a function? Yeah, that's FOIL stuff. So as we FOIL. If you want to, you could write it off to the side, negative 2 plus h. Remember, don't put puppies, negative 2 plus h. But you end up with 4 minus 2h. Minus 2h, good, minus 4h. And h plus h, sorry, h times h would be h squared. What can I do with that? Good. Then Karina, here's your part. What can I do? Back out the h. So we can go ahead and after the 4's cancel, we can factor out that h. We get negative 4 plus h all over h. Once those common factors are out in the open, I can go ahead and cancel them out. Technically reduce. I apologize, I shouldn't use cancel. I get a 1 on bottom, and now I have negative 4 plus 0 all over 1, which is 4. So the limit can get you to the specific one as well, directly, in that we could have the x's actually being plugged in for a specific x, which is good for solving the answer. The slope of the tangent line is negative 4. The only dilemma is, what if I was to say, okay, cool, what's the slope at negative 3? You're like, oh, what do we have to do? Go back to the beginning. How is that not as ideal as if we had just started with an x originally? If we had started with an x originally, instead of getting one number, we would have gotten one formula. And then you could have plugged in negative 2, plugged in negative 3, plugged in whatever you wanted. 2 different variations ultimately end in the same place. They both have different pros and cons.
How did you get that first one where you did it?
It was from the example that we did at the end of yesterday. Not the end, sorry, the beginning, the difference quotient. And I was showing you on the board really fast about how there is this spiffy calculus rule for taking a derivative, but we haven't specifically talked about it. So I'm like, if only there was a shortcut that we could memorize and solve, and it's coming. For honors, it's coming for regular house. It's a little bit too far for them. Did I finish? Oh, wait, pause. Do we need this page at all? Why not? Have we talked about derivative?
Yeah.
Yes.
Have we said that it's slope of a curve at one point, aka a tangent line? Have we written instantaneous rate of change? Go to where we wrote derivative. Put parentheses and say instantaneous rate of change. Then we can check that off. We wrote derivative. It was in big capital letters underneath the formula. And then, wait a minute. Haven't we basically just said the derivative is this guy? Okay, so we've done this whole page. We're just going to go down to the example. The book decides to cover them separately and basically cover the same thing twice, just kind of name it different stuff. Blah, blah, blah. Question. How do we find then, if they ask us to find the derivative, I know they're having too much fun with that. What are we going to do? They don't say tangent line.
Find one that works for all.
The one that works for all, we're going to find f prime of x, which means we're going to plug into the formula where we plug in x plus h as our input minus f of x all over h. I went a little fast, but my question is, do you see me plugging x plus h into my function. Do you see how I did f of x plus h and I did f of x? What's our goal? 0 over 0, keep going!
That's.
Yeah, so boil everything out, simplify everything out. Karina, I bet if H is going to factor out, and you'll solve, and maybe for tomorrow, if you do enough of these, you'll be like, wait, I think I see a pattern, and maybe you can figure out the rule without someone telling you. Bye, kids. See you later.
Bye bye.
Section 12.3 for tomorrow. Yeah, which is why we notes that. And I said theta, theta tan inverse. And then the picture. So the point has to be rectangle. So either I have to use 5 pi over 4 with positive or pi over 4 with negative. Does that make sense? Yeah. Good question.